The theorem is Poisson distribution is a limiting case of binomial distribution. In this theorem, we prove that if we take limits on the binomial distribution, then it converts into the Poisson distribution. So if we take n approach to infinity, that means the number of trial is large and the probability of success at each trial is very small, approaches to 0, and take np is equals to lambda, then binomial distribution tends to the Poisson distribution. So p is equals to, from here np is equals to lambda, then p is equals to lambda by n, and q is equals to 1 minus p, 1 minus lambda by n. And the binomial distribution x is the number of successes out of the n trials. So the probability mass function of binomial distribution is ncx, p to the power x, q to the power n minus x. We take limits n approach to infinity and p approach to 0 on this binomial distribution. Now we use the Stirling approximation. Stirling approximation used for n factorial when n approach to infinity. So any factorial number which is infinitely large, we use Stirling approximation. So limit n approach to infinity on n factorial, that is equals to this, right? So we take limits n approach to infinity on the binomial distribution, n factorial, x factorial, n minus x factorial. So n is infinitely large, so we use Stirling approximation on n factorial, that is equals to this. X, we don't know x is a small or x is a large. X, the probability of success is a small, so x is a small value. So x factorial is a small, so we don't use a Stirling approximation on x factorial. n is a large and x is a small, so n minus x is also large. So we also use Stirling approximation on n minus x factorial. So here under root 2 pi e raised to power n. Here is n. Now here is a n minus x, so I take here n minus x. Then n, here is n minus x, n plus 1 by 2. Then here is n. Now here is n minus x, so I write here n minus x plus 1 by 2. After the simplification, we get this. N minus x plus 1 by 2. I take common n from here, this, and get 1 here minus x by n, and get this result. Now we use these two results. Limit n approach to infinity, 1 minus lambda by n, n. Here is n, here is n. The answer is e raised to power this quantity. Here is lambda, so I write here e raised to power minus lambda. So if n approach to infinity, 1 minus lambda and alpha. Instead of n, here is for any other function which is not the function of n, the limit is equals to 1. So this is equals to e raised to power minus lambda and this is equals to 1. Here is n and here is x. X is not a function of n, so this get 1. So I get here these results and finally get the required probability mass function, which is a probability mass function of the Poisson distributions.